Hello, and welcome to my Pavilion talk. My name is Serge Leaf, and I'm a DARPA program manager. I joined DARPA about 8 months ago, and prior to that, I worked in EDA for my entire career, 28 years as a VP, 28 years at Mentor, last 10 or so as a VP. So now I work for DARPA, which is a pretty interesting place. It's been around for 60 years. It started because we were surprised by the Sputnik launch. And basically, there are a few little things that DARPA invented you may have heard of, like the internet, night vision, GPS, stealth flight, sensor fusion, autonomous driving, smart watches, voice recognition, advanced prosthetics, neural interfaces. So a lot of good stuff. So when you start working at this place, you feel pretty small once you start seeing the list of all the things that DARPA has done in the past. Basically, the way that DARPA works is we have an annual budget of about $3.2 billion. And this money is spent by around 90 appointed program managers who serve 3 to 5 year terms. And typical background as visionary academics, industry executives, and military leaders. And about 2 years ago, we got an add-on to our budget, $1.5 billion for something called Electronic Resurgence Initiative. This is not quite the Marshall Plan kind of money, but we're trying to infuse some energy into electronic design in the US. And since then, in last September, we got an additional $2 billion for artificial intelligence, and there have been another $2–3 billion here and there that have been dropped into the notion of the transitioning of advanced technology into deployment. So there are 5 technology offices at DARPA, and between those offices, between 75 and 90 program managers at any given time. So we're supported by about 100 government employees, about 1,200 contractors in the building, and we're running between 250 and 300 programs at any given time. And we're supported by thousands of university researchers and academics. So literally, there's this pyramid where 75 to 90 people drive significant research agendas. What I wanted to dig into when I started at DARPA are some problems that I've seen when I was in EDA that seem to have been unattended or at least ignored for some reason. Some of those reasons were market reasons, some were economics, some were technology. But basically, when I started thinking about what I would do if I had limitless amount of money, which is actually true, thank you, taxpayers. I started to think about how our industry really has evolved. And so back in 1967, we started integrating transistors onto silicon. And at that time, we thought that the practical design limit of things that we can create is about 10 transistors. And that was pretty awesome. And then in 1978, we started saying, okay, well, if we lay out transistors as a cell and replicate them a few times, that's really fascinating. Now we can build things that have 100 transistors. This is really great. And then in 1982, we suddenly started designing using logic gates as opposed to transistors. And now this is the time of 82, 86 era. Suddenly, we were able to do designs with 10,000 transistors. And that seems like incredible amount of logic. Hard to imagine how we could possibly use that. And then we had a breakthrough in 1987, 88. That's the emergence of logic synthesis. So now we could transition our design philosophy up to RTL, and our design productivity went way up. And now we started thinking we could do chips as big as 10 million transistors. This technology is going to carry us there. And so what happened next? And what happened next is really nothing. There have been no major revolutions in electronic design automation since logic synthesis. And modern chip designs that we're doing today already exceed this threshold of 10 million transistors that we thought this methodology could support. And so what's happening as a result is a lot of design methodology is currently broken. And that brokenness makes it really hard and expensive to design chips. So the design productivity is, I don't know if I'm blocking things, is the first thing to consider. So available gates, gates available to us have grown. However, the humans have not over time become more intelligent. And so we don't know what to do with those gates. And so our reaction was, oh, we're going to reuse IP now. So then the problem shifts into how do we integrate all this stuff. And we found that there's a lot of pressure and pain points when we try to bring this all together. I once visited a mobile handset company, and as I always do in customer meetings, I've spent first few minutes trying to understand what they do in this building, and there were 600 engineers in this building, and I started to say, oh, do you guys design the baseband processor here? No, no, they don't do that. What about the application processor? No. What about the modem? No. What about, and so after about 10 minutes, I ran out my knowledge, my totality of my knowledge about wireless handsets and what's inside was exhausted. I couldn't figure out what they do in this building. So I said, so what do you actually do here? And they said, we integrate a bunch of stuff that comes from other parts of the company. And I thought, this is pretty crazy. That's really not the solution to this problem. And so, sure enough, we started integrating IP around buses and other multiplex communication structures, and immediately ran into another set of problems. Well, we are not really utilizing on-chip communications effectively, and so that highlighted more issues. And of course, as we're designing bigger and bigger chips, verification becomes harder, and so there's a growing verification gap. So my assertion is that the chip design process is broken. It's way more expensive than it should be, and because of this, small and mid-sized companies are disadvantaged. They have a really hard time designing big and expensive chips. And the only parties that are capable of doing truly large chips are parties like NVIDIA, which is the biggest chip from last year that was discussed, 9 billion transistors, 8,000 engineering years, 4+ years to design. And I can sort of see that. And so because of this very high cost of designing sophisticated chips, we don't see small and mid-sized companies really capable of pushing state-of-the-art in chip design. And unimpeded by the economics of this, what we're seeing is in China, meanwhile, none of the factors that I've mentioned actually are playing a role at all, because China has a national fund, $155 billion. Until 2016, we thought this was all for improved manufacturing. But in 2016, we started seeing that actually a lot of this money is going into fabless chip startups. And this data is dated. It's from 2016, but we saw well over 1,000 fabless semiconductor startups, thanks to my friends at Mentor who meticulously collected and validated this data. Oddly enough, I got this from Mentor, and I showed around the government, and people from the agencies that one would think should know better, they look at this and say, wow, this is really good data. Where'd you get this? Merlin, thank you. So China is unimpeded by the economic and technology issues that I mentioned. And so maybe they're not doing designs that are incredibly cool just yet, but they're going to go through rapid learning cycles, and eventually, possibly very soon, there will be a substantial threat to US's electronic dominance. So what's happening in the US? Here's a picture of early stage funding, or actually funding for US fabless semiconductor startups. And what I did is I circled the A round here and marked in red the early round funding that was received by American startups. And what you see here is that between 2012 and second quarter of 2017, there's literally no investment going into early stage startups in the US. And so why is that? I sat on boards of several fabless semiconductor companies with venture capitalists who complained profusely throughout the entire experience about how did they ever get suckered into investing in the semiconductor company, because it takes $20 million before you know if any of this works. And for $20 million, they would repeatedly say, I could have 20 software startups or 40 internet startups. And so it is the perception and reality of high cost of getting to first working silicon that is really limiting interest by traditional venture investors in chip startups. So the way that venture capital thinks about the world is they sort of see they will give you $500,000 of seed funding to do proof of concept. Then they would give you $3 million to show them a working prototype. Then they'll give you $20 million when you're ready to engage with customers. But when you look at chip startups, all of a sudden what you see is that it costs $20 million to get to working prototype, and that is an impedance mismatch with the way that venture capital community thinks about this problem. So this is actually an ideal role for the government. This is where DARPA can step in and try to change this equation. So we don't want to be the venture capitalist. We do not want to be on the hook to fund the industry forever and pick winners and losers. What we would like to do is we'd like to change this equation to re-involve the venture capital in this segment. And so what my goal is with the new program that I'm running called ACE, Automated Implementation of Secure Silicon, is I have really two goals. Drive cost of getting to first working silicon to less than $3 million, and provide embedded security. So the dream in EDA, for as long as I've been involved in this, has been this concept of system synthesis, where you describe what you want at the system level, and then you ultimately implement it. But the reality is we didn't get system synthesis. What we have is something, this diagram here, I actually drew it up for a career day at my son's high school one day. And this is the grossly simplified EDA flow. And in fact, those of you from EDA know that this is grossly simplified. In reality, it's probably like 10 times more complicated. There are more boxes and all of this. So the process is still pretty much a manual process. The best thing that we've been able to do is we've been able to automate block level implementation. So we can, back in the late 80s, my friends at Synopsys came up with this banana curve, which I've used as visual aid for at least 30 years at this point, and probably owe them royalties for it. But the observation was that if the theoretical best was infinitely small chip that is infinitely fast, that was a good aspirational target. We further found that if you were to find a human designer that was like a god of IC design and give him infinite amount of time, he could come up with a design that was really small and really fast. And then when we started doing this automatically, we found that, well, we can create in a single day multiple solutions on this curve. None of them will be as good as the human designer, but they will be maybe good enough. And so as time went on, this improved, and the banana curve got closer and closer to the human designer. And until now, we've reached a point where it makes no sense really for humans to do block level design in large number of cases. Basically, there are still limitations. Because we can only sort of do this to one block at a time, the chip design process is really costly. It's kind of interesting when I show the startups this number that it takes $30 million or more to get to first working silicon, they all tell me, no, it's more expensive than this. And when I say it's 9 to 12 months to design a chip, the defense guys that I talk to say, no, you're way off. It takes twice as long as this. So, but somewhere in there is the truth. And there's many human-introduced errors that are in this process, and the power is really not easy to predict, and security is absent from most modern designs. So, thus, we come up with this ACE program. And the approach ACE takes is we would like to incorporate security into next-generation chip designs. And while we're doing this, we also want to create automation that would enable us to improve the design process and really use techniques that are a combination of novel and not so novel, but integrate them together to drastically improve the efficacy of chip design. And so the approach in ACE is basically platform-based design. where we have the notion of a platform, which is made up of generators that can be parameterized to produce a general computing portion of the chip. And it is combined with a security engine generator, which can, based on the requirements, produce security partition of the chip. So if we can, this is basically the goal of the ACE program. Automate the inclusion of scalable defense mechanisms into chip design to enable security versus economics optimization. And if you look at, if you think about security in a fairly traditional way, so you know that in some cases putting up a lawn sign that you have a contract with security company, that's enough to dissuade certain type of attackers. And then, according to the movies anyway, Fort Knox level security is not enough to dissuade some kinds of attackers. So the point is that there isn't a singular security strategy. The security strategy is driven by the economics of your application. So the idea behind ACE is to automatically create different security mechanisms that are correlated to the economics of your problem. So I mentioned system synthesis before, and back to my visual aid. The goal has always been, I think, in EDA, is to synthesize this whole SoC that I showed earlier in my example, not just one block at a time. And if we were to synthesize this, the well-understood science behind it is we want to explore the trade-off between performance and size. Well, we haven't been able to do this at the SoC level, and yet the problem has changed. Because now what we really want is to actually synthesize something like this, not just exploring performance and size, but now we have to add power to all of this. And before we solve that problem, the situation has gotten even more complicated, because now we actually also want to add security to this. And that means another dimension to this optimization curve. And then when you start thinking about it, security actually isn't a one thing. There are multiple attack surfaces that we care about. And so now, all of a sudden, we're looking at this, and it's starting to look like 7 dimensions worth of optimization. So it's an interesting problem, and there are some interesting challenges that go along with this. For instance, how do you even quantify security? Security is such a vague concept. How do you know that something is more secure than something else? How do we quantify this? How do we rapidly estimate the resistivity to different types of attack? And how do we optimize it against on a 7-axis system? And so that's what we are trying to achieve with ACE. But before we go any deeper into this, what is security? So in order to even start thinking about this problem, we had to reach agreement even within DARPA. What do we mean by when we talk about on-chip security? And so I looked at this. Okay, so in the software world, there's a lot of investment in cybersecurity. In fact, it's a multi-billion-dollar business. Lots of companies are doing a lot of work. Universities have been done with this, I think, 20 years ago. They lost interest. It became a solved problem, right? Or maybe you guys are still doing something about software, yeah? Okay, good, keep it up. But I said, okay, this is already well attended to. I don't need to do anything about this. Then we started looking at, okay, so what happens on the boundary of hardware and software? Yeah, there's a lot of interesting stuff happens, lately in particular. But we are already investing in this area. So we have a program in DARPA called SITH, which focuses almost exclusively on hardware-software interface. So that left me with the hardware attack surfaces. So the attack surfaces that ACE cares about are as follows. So the first thing is side channel attacks. What are side channel attacks? Side channel attacks is an extraction of secrets through physical communication channel other than the one that was intended by design. And here, we have to make a relatively cynical assumption that all the outer defenses have been broken, and the attacker can listen to whatever our chip is emitting. The next attack surface is reverse engineering. This is extraction of algorithms from illegally obtained design representation. It could be that somebody walked out with a netlist, or they went through a lot of trouble to reverse engineer, decap, delayer, and so on. It really doesn't matter. In ACE, we make an assumption that the attackers have access to the design files. And then supply chain is the next attack surface that we care about, and this is cloning, counterfeiting, recycling, remarking, overproduction, and so on. And here we have to make an assumption that the attackers can make perfect clones. And then the last one is malicious hardware. This is about insertion of secretly triggered disruptive functionality into the design. This is the most depressing one because there's least we can do about this particular set of attack vectors. And here we almost have to assume that the attackers have already made it into our chip, and now we have to figure out how to recover from something like this. So who are we trying to help with this technology? So I look at this program from the position of who are my customers. You can't really beat 28 years of mentor out of me all that easily. So who are my customers? So I kind of look at these 4 groups who are plausible customers for this. And the first group is huge semiconductor companies. But are they really my customers? They're already investing an incredible amount of money into making their chips secure. They have huge businesses to protect. They have massive liability exposure. So when you look at companies that I listed here, they have hundreds, if not thousands of people that are doing nothing but incorporating security into their high-volume silicon. And then when you look on the other side of this, the system integrators, what about them? These are people who make your intelligent lawn sprinklers, internet-enabled door locks. They really don't care about security at all. They care about time to market. They care about eye candy that you see on your smartphone. And if they could spend negative amount of energy on security, they would. So that basically leaves us with these 2 groups in the middle that represent the target area for ACE. So first group is mid-sized semiconductor companies and systems houses. These are people who are loosely aware of security issues, but do not have sufficient economic motivation to do something about it. And some large companies sort of fall into this category. And by do something about it, I mean invest hundreds of engineers to solve the problem, because that's really the only strategy that is currently available. And then there's another group, which is defense contractors. They definitely have pockets of expertise. They know how to make things secure. But there's typically very few true experts in that world, and they're very valuable. And what we get from defense contractors is very inconsistent from the security perspective. And they also view their security expertise as some kind of black magic and art. They really don't see how publicizing this type of learnings to the masses is benefiting them. So our goal is, if we solve the problem for these 2 constituencies in the middle, maybe we can tell the big semiconductor companies, you don't need 4,000 engineers on this. Maybe you can get away with 2,000. Maybe we can tell people that are doing intelligent lawn sprinklers, hey, you don't have to put any effort or money into this. We will make your silicon secure. And so the idea is to start in the areas where we have the greatest needs and then spread out to adjacent markets. So what we're doing with ACE is we define this the program that has 3 thrusts. So one thrust is on-chip security. We want to incorporate security right into the chip design. What we want to do for on-chip security is we want to be able to do authentication, provisioning, monitoring, and enforcement of security policies. The second thing we want to implement is the security tools. In other words, how do we obfuscate, watermark IP, for example? Can we simulate the attack vectors that hackers today perform in the labs? Can we do threat analysis? Can we look at IP and say, this may have suspected Trojan or it may not? And then the last thing is, how do we bring all of this together? How do we bring general computing and security partitions together? And that sort of involves silicon platforms, generators, interconnect synthesis, and optimization. And so integration of all of this is a key challenge, and the basic goal is for ACE to democratize chip security through automation. So our approach to chip security is like this. We sort of think of this as there's an outer perimeter and there's the inner perimeter. So the outer perimeter is, so think about this as an analogy. The barbarians have swum across the moats, they climbed the walls, and they're in our courtyard. We are defending the iron cage in the middle of the courtyard. So there are a lot of technologies and parties that are trying to build higher walls, bigger moats, and other deterrents. But in ACE, we make the assumption that the adversary has already penetrated all of those. That means I'm not discouraging people building bigger walls. Good luck and Godspeed. I hope they never pass the walls, but we have to make an assumption that they're already in the courtyard and we're protecting the courtyard. So we're focusing on the inner perimeter. And in the inner perimeter, we are basically looking at these attack vectors that I described earlier. And the way we sort of see dealing with this is by creation of an on-chip security engine that is the central nervous system for coordinating security activities, the defense mechanisms and countermeasures. And then in some cases, we need support services outside of the chip in order to facilitate the workings of things inside the chip. So one way to think about it is in this example, you have a canonical SoC where you have a memory, CPU, and some number of peripherals. And so the way to think about security is, okay, so we can create security in layers. So the entry layer of capability here might be hardware root of trust and the key store. So this kind of feature takes relatively little silicon area, has a small impact on performance and power, and it gets us something. It gets us some defenses against supply chain attacks. But that's just the beginning. So maybe at the next step, at the next level, we start thinking about provisioning, obfuscation, logic locking. So now we can lock and unlock, encrypt and decrypt different blocks of logic. So now we have greater security capability. And then you can basically go crazy here and say, okay, in level 3, we're going to start including silicon odometers. So we can count boot cycles or read writes or whatever. We can start doing Trojan detection and bus monitoring. And then maybe at level 4, we can start looking at authenticating IP blocks that are in the chip. And on and on and on. At level 5, you can really go crazy and start encrypting all the on-chip buses. Now, this is really expensive. It's unlikely that anybody would find costs associated with encrypting all the buses a practical matter. But on the other hand, if you have a domain that you want to make secure where there's 3 participants, it is not implausible to create a secure domain on an otherwise non-secure multiplex communication framework. So, and then, of course, because we're dealing with evolving threats, we have to assume that over time, we need to be able to upgrade policies in the security engine, and we also may want to do hardware upgrades. So inclusion of some kind of programmable logic block in this may be a good idea because we may want to do hardware upgrades to the security engine. And so what I showed here, incidentally, has absolutely nothing to do with what we told the proposers to put together. This was an artist's conception of what it could look like, but I'm very happy with the community that formed around ACE and then took this as sort of a starting position and then came up with great and original ideas as to how to accomplish this type of tasks. And I found this is actually one of the biggest challenges in being a DARPA program manager is when I try to write the BAAs is to specify things just to a certain point and then back off to enable the community to apply its creativity to this rather than forcing them into particular solution strategy. So, so what about the incoming IP? How do we deal with all that? So one thing that we've been looking at is the notion of IP watermarking. So a piece of IP in source form inside the Synopsys building may be trusted today. Tomorrow it gets encrypted and shipped somewhere to some customer, and the day after a malicious employee walks out of the building with that RTL. This starts traveling around internet. The state machines could get modified, could be additional if-then cases could be thrown into this. Trojan triggers. And then at some point it ends up in front of a designer who's about to incorporate this IP block, which he thinks to be genuine, into his design. And sure enough, it looks genuine. It still passes the original test suite that came with this, but what else does it do? How do we know? And so one idea that we're looking at is the notion of watermarking. Can you create a watermark for a piece of IP? Can you incorporate this watermark as, say, electronic circuits right into the design so that it instantly detects, it can be forced to detect if the design has been modified, and it should be extractable through simulation or from live silicon. Another thing that we've looked at is the notion of threat analysis. So in other words, if you examine IP and you observe that there's an island of logic that is very inactive relative to the rest of the RTL, what does that mean? That could be a Trojan, but it could also be what the designer intended, so false positives are possible. Or what if there is a chunk of logic that takes very special set of circumstances to activate? That also kind of smells like a Trojan trigger, but it could well be exactly what the designer wanted. So there are some interesting opportunities here for machine learning, because a human ultimately has to tell the difference between real positives and false positives. And then there's the notion of, is it possible to simulate what the hackers do in the lab? I mean, today, what happens typically is people make their SOC, and they put it in a manila envelope with a check for $200,000, and they ship it to one of about a dozen companies in the world. And then 6 weeks later, they get a report. This is what we've been able to extract from your chip. So the question is, can we take one of those hacker labs and turn them into a simulator? Can we build a simulator that does exactly what they do, but takes our design in a form where we can still fix it? In other words, not physical, post-manufacturing thing. But can we give them our RTL or gate level design or layout and do it overnight? So that would be interesting. And this fits very nicely into kind of EDA-ish flow. You have a design, you have a tool, you drop one into the other, you get some kind of answers of value. And then lastly, the reverse engineering. What can we do with reverse engineering? And here, our strategy is all about obfuscation. In other words, logic encryption, taking beyond the limits of good taste, and that's been an active research area for at least a dozen years, and there are very compelling solutions now, and we don't intend to reinvent good stuff that's already come around, but rather figure out how to leverage it in this context. And then, how does ACE work? So the way we sort of structure this is in phases. So in phase one, what we want to do with ACE is something called assisted composition, where the starting point is a bunch of IP blocks, which represent a mix of general computing and security, and then we run a tool on all of this, and then all of this stuff gets integrated into a bus. So I know what you're thinking. You've seen this slide in 2005. I know I had a product in 2005 that did this. So not terribly interesting. Automated integration of IP into buses, a generation of bus interface logics, a generation of device drivers. Great. I know it's been done, but this is a necessary step in this direction. And so next step is automated composition. Now what we have is the notion of a platform generator, which offers you essentially configurable domain-specific hardware foundation. And then the user essentially selects or parameterizes this platform, and then he pushes a button and out comes an SoC that is also, now you have ability to separate the general computing and security module. Now you're probably thinking, oh, I've seen this in 2010, 2012. Yes, you have, and this is the generator strategy that actually is even older than that. In the 1990s, we were dicking around with this stuff. And again, necessary step. This is where we get to something that's actually interesting. So the next step is where we think that ACE can do something truly different. Now, we effectively say, we want to start with this platform, and here, as a designer, I'm going to provide a cost function to the tool, which says, the importance of performance to me is 2 on a scale of 1 to 10. The importance of size is 9. The importance of power is 3, and then I provide parameters for security. And now we have a tool that takes all of that in, generates billions of solutions, out of which maybe 4 are close to our desired goal. And basically, we explore huge solution spaces against the 7 dimensions of optimization. And so now we're looking at something that is pretty revolutionary. Those first two stages I described, they're incremental stages that we built upon. So how do you establish a cost function for something like this? So we started back, as I said in the beginning of my presentation, with the notion of performance versus size. And I imported this picture from the 80s. This is simulated annealing. I'm envisioning that something like this can still be used. It's just on more dimensions of optimization. But what we need to do now is we need to extend the cost function so that it's not just performance and size, but it's also power and security. Power computation is really hard. We know that in order to get real numbers about power, you need to go all the way to layout, and then maybe you have something approximately close. We don't want that. We want to be able to do power estimation. We want to be able to say architecture A is better than architecture B. So in short, we want to have relative assessment of power, not absolute assessment of power. And security is even more complicated because we don't even have a particularly good definition for security. And so how do you know whether one thing is more secure than another? That's a good challenge for the community to come up with a way to estimate security. And then when you start thinking about cost functions, so how do you design a cost function for something like this? So I would say if I'm designing a lawn sprinkler, I could say, well, maybe performance is not that important to me. Maybe size is important if my design is successful and I'm going to go to high volume. Maybe power is really critical because I want this thing to run for 12 years on a single battery. And security is that don't care. Who cares about attacking lawn sprinklers? Then if I'm forced to think about this a little bit more and expand the security function, now I'm thinking about the lawn sprinkler and I'm saying, okay, side channel attacks, really, I don't hold any secrets, so I still don't care. Reverse engineering, still don't care. Supply chain, now that maybe I care about, because if I'm really successful, somebody can knock off my ASIC, and they can really damage my business. So I'm going to say, I do care about that one. That one is important to me. And that becomes one of the directives to optimization. So the design that I would get as a result of this kind of input cost function would probably have a PUF and a unique identity management system that surrounds a PUF. It would have to incorporate enrollment and authentication capabilities, which would be the basic defenses against this type of attack vector. But how big a PUF? Well, that depends. I said that size actually matters to me. So now the system may be forced into some compromises in terms of how big a PUF I can afford. Anyway, so moving on, how do we measure success in something like this? So supply chain attacks, so supply chain attacks are essentially, as I mentioned before, I really like this graphic where you look at a bunch of chips you buy from a distributor, but then you subject it to X-ray and you see, wait a minute, one of this is different. I wonder why it's bigger. Is it bigger because it was done on trailing edge technology node, or is it bigger because it actually has something else that it does? We don't know that. We really don't want to see this happen. So what we care about is cloning, recycling, counterfeiting, remarking, offshore overproduction. And so our strategy to deal with this is the notion of inclusion of hardware root of trust, support for locking and unlocking, so enrollment, authentication, provisioning, and so on. And so if you look at the metrics of this, my team at Mentor actually tried to do this manually to implement this kind of capability. And so our experience was that it took us 9 months and about $2 million to create this solution manually. And what I want ACE to do is to create this kind of solution automatically. And furthermore, with ACE, I wanted to be able to create multiple different solutions and allow the designer to really travel along the spectrum to find a solution that fits the economics of his problem best. If we look at side channel attacks, so what's a side channel attack? People listen to emissions, they find the crypto and they start looking at what happens to the crypto core. And so what we're basically talking about is an interpretation of emissions. We have really only two strategies to deal with this kind of attacks. We can try to design circuits that don't emit. In other words, we have to design a circuit in such a way that for every active transistors, there's a transistor that's not active to cancel out the active transistors. That's really hard, incidentally. Or we can have a design produce so much noise that you can't tell the difference between whether it is or is not hitting the right keys. So again, if you look at sort of licensing some IP, it costs today a couple $1 million and about 6 months of calendar time to do. I want ACE to be able to do this automatically. And furthermore, I want ACE to be able to essentially give you options of automatically implementing different side channel attack resistance strategies. So we know that creating equivalent counter gates costs you 100% penalty in size. And we know that creating power emissions to mask the real power emissions will cost you 2x in power. So none of this is free, and you as a designer need to decide where you're comfortable with being on this curve. And so then the next one is reverse engineering. This is where people take designs and somehow access the design files and then interpret what they mean algorithmically. Algorithm extraction is what we care about, and really the only strategy that we have against this is logic obfuscation. And there are multiple logic obfuscation strategies, and we have some people in this room who have spent their whole lives on logic, encryption logic obfuscation. And so I actually have, once in my life, encountered a human obfuscator. So I was at this defense contractor, and I asked this customer, I said, so how do you guys do this anti-reverse engineering? And they said, oh, we do logic encryption. I said, what tools do you use? And they said, oh, we don't use any tools. We have Fred. Who's Fred? Oh, Fred is this guy that takes the design and then he injects all these key gates, and then he creates the key register and he routes everything. And it's like, Fred, how long does it take Fred to do this? 6 months. There's no reason, we don't need Fred. Fred should be doing more productive things for society. And so what we really want is we want to be able to automatically create these different solutions here that provide us with a low, medium, and high degree of resistivity. So if you sort of look at the spectrum of things that we could do, we have kind of a simple logic encryption where you insert a single key gate for each key bit. And then logic obfuscation, where you insert more of those things, and then you have multifunction elements. So instead of XORs and XNORs, you now insert elements that can be multiple things. And then until you get to the notion of overloading state machines. And every one of these things has different costs, different economics. And so my assertion is the economics of the solution have to gel with the economics of the end application. And that's what we're trying to enable the customers to do automatically. And this I really didn't want to show. This is the most depressing one. It's about Trojan detection. And unfortunately, that's the one where I feel we can make the least progress. And the part of the issue here is that Trojan detection is hard. Trojans are unknown unknowns. So search for unknown unknowns is pretty hard because you don't know what you're looking for. So the best we can sort of hope for is do runtime Trojan detection. We can monitor on-chip communication structures and look for triggers. And in ACE, we have a lot of activities proposed in this area. How do you runtime Trojan detection? But keeping the Trojans out is a really hard problem. So you have the payload, which we don't know how to detect, and you have the trigger, which we may have a shot at detecting. So we're going to try to detect triggers. So what we did with ACE is it's I don't know, my math is not really working right now, but it's a 3-phase program, I think about 4 years. And it's arranged in this sort of fashion. And so exiting phase 1, we want to be able to do a complete SoC design based on the ACE technology with this listed security mechanisms in 3 months. Exiting phase 2, we want to be able to accomplish the same thing in 1 month with a lot more security features. And exiting phase 3, we want to be able to do a complicated SoC that is fully secure in 1 week or less. So that's basically the program vision. We've put a lot of effort into recruiting the community for ACE before we even got started, trying to get non-traditional parties to participate in this. And right now, we are in the source selection phase. So I think by the end of summer, we will announce the teams that we'll be working with going forward. But this is just the beginning. We're also looking at security DRC, which may be a next program in this area. We're also looking at some really crazy stuff like using human immune system as a model for hardware security. And I'll be putting out some challenges in this area as well. This is just the beginning. We know that on the security side, we're just doing some very rudimentary things, but there is really nothing in place right now, so I feel like we have a chance to move the needle somewhat. And there is opportunity to go a lot deeper than where we've gone so far. But the point, if there was one point I'm trying to make, is there is no singular security solution to every application. Security has to gel with the economics of the application. Because if the security solution is too expensive, people are not going to adapt it if it doesn't fit into their economic model. That's it. Thank you.